Now, let us further look at characterization of systems along these two lines. So, that is we want to look at characterization of systems in terms of impulse response duration. So, the impulse response duration can either be finite or infinite, and if the impulse response duration is finite, this is called finite impulse response, and this is denoted as FIR. If the impulse response is infinite, just paralleling what was given earlier, this is denoted as infinite impulse response and abbreviated as IIR. So, as far as discrete time systems are concerned, among the class that we are interested in, FIR and IIR systems are an important sub classification. Now, let us look at this simple difference equation. Y of n equals a times y of n minus 1 plus b times x of n, and then we will assume y of minus 1 to be 0 and let x of n be delta of n, and then to satisfy the mathematician we will assume a naught equal to 0. Unlike differential equations which are more difficult to solve, difference equations are easy to solve. All you need to do is start evaluating y for various indices. For example, if you look at y of 0, this is a times y of minus 1 plus b times x of 0, and y of minus 1 is 0 as per this assumption, and x of 0 is for this given input is 1. Therefore, y of 0 is very simply b. Similarly, you can find out what y of 1 is. So, you can recursively evaluate this difference equation and quickly see what the pattern is. And if you did this, you will be able to see that y of n is b times a to the n, and for n greater than or equal to 0. Okay. And it is easy to see this particular system, that is y of n equals a times y of n minus 1 plus b times x of n. So, clearly the input x of n is delta of n, which is the impulse. Therefore, y of n that we have obtained here is really not y of n, but h of n, because we always use the special notation h to denote impulse response, and this is what it is. It is easy to see that h of n is, just let us go back and look at the classification we have given in terms of impulse response duration. Is this IIR or FIR? So, no, whatever it is this IIR or FIR? That is the question. This is indeed IIR, because b times a to the n is of infinite duration. At no point does this become strictly 0. You should not look at it from the point of it decaying. For example, if mod a were less than 1, that it will decay quickly and beyond a certain point reach a level that is practically 0. That is not the kind of classification we are after. We are looking at it from a theoretical point of view. So, this is clearly an exponential that lasts forever for n greater than or equal to 0, and hence this is IIR. Now, the question to ask is, by looking at the difference equation, can we make some general statements regarding the system being IIR or FIR? So, clearly the system is IIR in this particular case. Now, let us look at this particular example. Y of n is b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. So, this is the input output relationship, and what is h of n? All you need to do to get h of n is replace the input x of n by delta of n, right. H of n is the impulse response, x of n is the input. Input has to be the impulse if you want y of n to be h of n. So, h of n in this case happens to be b naught delta of n, b1 delta of n minus 1 plus b2 delta of n minus 2, okay. And this system is clearly IR or FIR? FIR, because the impulse response consists of 3 samples. Starting at n equal to 0 it is b0, at n equal to 1 it is b1, at n equal to 2 it is b2. So, this is a system whose impulse response is of finite duration. So, this is an FIR system. Now, if you go back and look at this general equation, you can see that if all the AKs are 0, then the system is FIR, very easily seen from this. That is, if all the AKs are 0, this implies system is FIR. Now, let us go back and look at this IIR example that we saw. We know that the system is IIR based on the example that we just worked out, and we see that if the system is IIR, at least one AK is non-zero. all right. So, if the system is IIR, at least one AK is non-zero. So, now the question arises, if one AK is non-zero, does it mean the system is IIR? Notice carefully what statement we are making here. If the system is IIR, at least one AK is non-zero, and the previous statement is just the contrapositive of the bottom statement. A implies B, the contrapositive is not B implies not A. Therefore, at least one AK is non-zero. The converse of that is all AKs are 0. So, not B implies not A is IIR becomes FIR. So, these two statements are, one is the contrapositive of the other, but what we want to ask is, if at least one AK is non-zero, does it mean the system is IIR?